Hello everyone, Dr. Young here, and in this video we're going to talk about epoxides, opening them up under acidic conditions, and we'll kind of compare and contrast how they're similar but different to basic conditions. So if you're in acidic conditions, what you're going to see, right, is with your nucleophile, you're going to see something like H+, or maybe H2SO4, or some other acid. You're going to see some sort of acid, and the idea is that these acids are going to be in a catalytic amount. Right, so you're going to see either cat written next to it or like 5%, 1%, something like that. And if you look over at your actual epoxide, we're going to treat these as just like so many other reactions we've seen, right? If you look at your epoxide, the oxygen's partially negative, this carbon's partially positive, partially positive. If you look at what I've got as far as my reagents go, I've got methanol, which we know is a poor nucleophile. And in this specific example, I gave you H+, which is just some generic acid. Because the identity of the acid is not super important, just that it's not nucleophilic. And I wrote cat for catalytic. So now in the basic conditions, right, hopefully you've already seen the ring opening under basic conditions video, right? The basic condition video, we had a good nucleophile that attacked our epoxide and forced it to open. In this case, I have a poor nucleophile, so it's not going to be able to attack the epoxide and just open it as quickly, right? What we're going to see instead is that I'm going to protonate my epoxide, right? So I've got a fully positive hydrogen that's going to be attracted to my partially negative oxygen. So our first step is that we're simply going to protonate the oxygen. And that's going to give us our epoxide just protonated. Boom. Now, just like we do in other like ether reactions or alcohol reactions, right? Basically what I've done is I've taken that oxygen, which was not really a great leaving group because it'd be O-, and once I protonate it, I make it a better leaving group, right? Oxygen does not want to be positive. It wants to take electrons back from something. It could kick that H back off, which is going backwards to the parent epoxide. Or we could break one of these two bonds here, is the idea. Right, so I could either break this bond on the left to get electrons back, or what I could do is I could break the bond on the right to get the electrons back to the oxygen, and that's going to open up the ring. Now, if I break it to the right, this right-hand side, what I'm going to get is an O with the lone pairs back in the hydrogen, and this carbon right here is now going to be the one that picks up the positive charge, right? So if I label these carbons 1, 2, 3, and 4. We're talking about carbons 1, 2, 3, and 4. So I've opened up the epoxide. If I go the other direction, the one in green here, I open up on the other side. I'm going to end up with the alcohol on carbon number 1 here, 2, 3, and 4. And my carbocation is going to be on carbon 2, right? So these are kind of my two options as far as like which side is this epoxide likely to open up on. And now if you look at these, right, hopefully you should look at these and say, ooh, well wait, one of these carbocations is way more stable, right? Because over here we have a primary cation, and over here we have a tertiary cation. And which one's more stable, right? Definitely the tertiary carbocation is way more stable. So more stable. So that means this is going to be the correct route that we go to, not this route, right? The epoxides are not going to open up leaving a cation on a primary carbocation. They're going to open up and leave a cation on the tertiary one. And so we have the epoxide open up so that you have a cation on the tertiary carbon, and now it's kind of like an SN1 reaction in a way, just that we have a carbocation and something can add. Now this is when my methanol can add. So I've got a CH3, OH, and now my methanol can add. So it's going to attack the carbocation, giving us this intermediate. Where we have the OH up top and the OCH3H+, this oxonium ion. And again, oxygen doesn't really want to be positive, so this is going to lose an H. That H is going to be picked up by something, solvent molecule or another epoxide or something like that, to give us the final product, where I've opened up my epoxide. So I'll have a OCH3 adding opposite of where that alcohol was. And so this would be my major product, right? So what I've done, you'll notice, is that my nucleophile, and I'll write this in a different color just to emphasize it, right? What's important is that under acidic conditions, so here's my big star, the nucleophile, the nuke adds to the less substituted carbon. Right, to the less substituted carbon. That's opposite of when it was under basic conditions, right? Under basic conditions, the nucleophile added to the more, sorry. Let me erase it. I'm glad I said this, right? It didn't add to the less substituted, it added to the more substituted. The nucleophile adds to the more substituted carbon. Remember, under basic conditions, the nucleophile added to the less substituted carbon because it was just easiest to get to. It's kind of a SN2-like mechanism. In this one, though, since you're protonating the epoxide and you start to open it up, as you start to open it up, that carbocation is going to start forming on that more substituted carbon. And since it's starting on that, it's forming on that more substituted carbon, that's where the nucleophile is going to be attracted. And so the nucleophile adds to the more substituted carbon under acidic conditions, adds to the less substituted carbon under basic conditions. So let's take a look at some examples. Also, just while I'm here, I want to make a note that they do add anti still, right? Because the idea is that this alcohol is kind of hovering over this carbocation, and you're kind of going back and forth between these two things. Let me draw this in green here, right? That this is almost like a resonance structure where some of the lone pairs from that oxygen are donating electrons into that that carbocation. It's kind of like your bromonium ion or the, if you remember during with mercury, when you did oxymercurations, it's the same kind of idea. So they do still add anti, just like we saw with the other example. So let's take a look at some of these here. So here I have ethanol with acid, right? So I'm seeing that, oh, hey, look, we have an acid. This is my nucleophile. So since it's acidic, I know that I'm going to add my nuke to the more substituted carbon. So I'm just going to redraw my product here. Right, my epoxide was here and here. And so instead of drawing my epoxide, right, so here's, I'll just write carbons 1 and 2, carbons 1 and 2. Since I'm going to add my nucleophile to the more substituted carbon, that means my nucleophile should end here. OCH2, OCH3. OCH2, CH3. And then my OH will be on carbon number 1. So I added my nucleophile to the less substituted one. Now note that we have a chiral center here, so this is actually going to give me two different products. I don't have, actually, should I? Nah, let's not worry about this right now. Don't worry about that right now. I didn't show any stereochemistry in my parent epoxide, so don't worry about stereochemistry here. If I did have this chiral center right here as a dash or a wedge, then we would need to be concerned, but that's not in this example. Let's just forget about it. So this would be my product. If you don't show stereochemistry, that implies a mixture of isomers. This also works here, right? So now I'm adding HCl, which is the acid, but it's a nucleophilic acid, so I've got H plus and I've got Cl minus, which is my nucleophile, so I've got a nucleophilic acid. It's going to do the same thing, right? You're going to go protonate your epoxide and you're going to add your chloride to the more substituted carbon. So we're going to end up with something that looks like this. So I've added my chloride to the less substituted carbon, to carbon 2 in this case, right? Carbons 1 and 2, carbons 1 and 2. And again, they would be anti, there's no stereochemistry here, so you don't really see it, but it adds to the opposite. And this last one, I do have stereochemistry to worry about here. So let's take a look at this one. I'm on a ring, I've got dashes and wedges, so very definitely that epoxide's on the top face. I've got a methyl on the bottom face going away from me. I'll label these carbons 1 and 2 here. Carbon 1 and carbon 2, I've got a, carbon number 1 is a secondary carbon, carbon number 2 is a tertiary carbon. So I know that I'm going to add my water to the tertiary spot here, right? So if I go and I draw my product, I've got my cyclopentane. We'll call this carbon 1 and carbon 2. Carbon 1, right, so the idea is that this is going to have an H on it, and this oxygen is going to be positive, and my water is going to end up on the more substituted of those two carbons. So when this breaks, when this opens up, my oxygen is going to be on the top face. My OH eventually is going to be on the top face. And then, so that means my water then, in this case it's my nucleophile, my water is going to end up on the bottom face, right? Because it has to attack from the opposite side of where that alcohol was, where that epoxide, that protonated epoxide was. Now this CH3 here, this methyl that was a dash, that means it got pushed up into being a wedge. So now it's a wedge because it kind of gets forced up into that position during those transition states and intermediates. And so this would be my product for an example like that. So it's similar to the basic conditions in that they're both anti-additions, right? So always anti-additions. They're always anti-additions, right? So that you've got one thing on top and one thing on the bottom. And I'll just emphasize that with this example, right? So anti-additions as in that OH is on the top, this OH is on the bottom. What's different, again, is that under basic conditions, the nucleophile goes to the less substituted carbon. Under acidic conditions, the nucleophile goes to the more substituted carbon. That's the big difference. So I hope you feel a little bit better about what acidic conditions look like when you talk about ring openings for epoxides. If you have any questions or comments, leave them down below. Have a great day.